Hello. As we mentioned with polynomial sign charts, in calculus you will most likely use sign charts to help you analyze the behavior of a function. In this video, we will use our prior knowledge of sign charts and what we have recently learned about rational functions to construct a sign chart for a rational function. So let r of x equal this rational function, construct a polynomial sign chart for r of x, and then use it to create a possible sketch of the graph of r of x. So we'll start by factoring r of x. We know that helps us to identify things like x-intercepts, vertical asymptotes, and holes. So in the numerator, we're going to take x squared minus 6x plus 8, and that's going to factor to x minus 2, x minus 4. In the denominator, we can factor out a 7, so of x minus 4. And then we have the x plus 1 squared and x minus 6. So with polynomial functions, we were interested in including all of the x values where the function equaled 0. And now with rational functions, we must include not only the x values where the function equals 0, but also where the function is undefined. So let's start out with the values where the function is undefined. So r of x is undefined when the denominator equals 0. So we know the function is undefined at x equals 4, x equals negative 1, and x equals 6. And one important thing to notice about x equals 4 is that that's actually going to be the location of a hole. And so when we're making a sign chart, we want to know where the graph changes from positive to negative. So one thing we're going to do is determine the location of that hole to see if it's even in an area where the graph might be changing from positive to negative. So recall, one way we can identify the location of the hole is to consider the limit of this simplified version, which again, I've mentioned a couple times is in other videos, is not the same as the original function, because this simplified version would not have a hole, but it at least allows us to see where the hole is. So once we cancel out that common factor of x minus 4, we can actually substitute 4 in for all of those x values. And when we do that, I'm going to let you check, but we do get 7. So the hole is at 4, 7. And as I mentioned a moment ago, we're really interested in the sign chart where the graph is changing sign from positive to negative. And this hole at 4, 7, that's not near the x-axis really. So we're not worried about the graph changing sign near 4 and 7, which means when it comes time to graph or sketch our sign chart, we're going to focus just on x equals negative 1 and x equals 6. And in fact, we know that those are going to be vertical asymptotes because those are the values of x that made the denominator equal to 0, but not the numerator. But as with any sign chart, we do want to know where the function equals 0. So we know that this this rational function will equal 0 when the numerator is equal to 0. So we're going to look at x plus 3 squared, and that would equal 0 at x equals negative 3. And then we also have x equals 2 is another place where x equals 0. And then as we just analyzed, x equals 4 is actually not a location where the graph of r of x equals 0. There's a hole at 4, and that hole is actually near an output of 7. So I'm not even going to include x equals 4 in this list of values that make the rational function equal to 0. So these are in fact the zeros of r of x. So on our sign chart, we are going to plot. Well, first we're always going to label. Remember, in calculus, you're going to have to label a few things. So we're going to get in the habit of labeling this one just the sign of r of x. I'm going to plot the zeros. So there was a 0 at -3. There was a vertical asymptote at -1. There was another 0 at 2. And I just noticed that I had an error in this problem, so we're going to go back and fix this. I had a silly little copy error. The original said x plus 6, so if you were wondering what was going on, that was me just making a silly mistake. So the vertical asymptote, the other one would have been at x equals -6. So let me redraw my sign chart so that I have some room here. And we'll plot again anywhere the rational function is 0 or undefined. So we're going to have our first vertical asymptote at -6. Then there was an x-intercept at -3. And then there was a vertical asymptote at x equals -1 and an x-intercept at 2. And what we will do is we will analyze the sign of this polynomial or this rational function on each of these intervals. So we'll start with picking any value smaller than -6. I'll just use a test point of -10. So if we were to evaluate r of -10, we have 125, which is positive. -10 plus 3 squared is positive. And then actually let's focus on this factored part. So x minus 2, if I let x equal -10, that's negative. And then x minus 4, if x equals -10, that's also negative. Moving on to the denominator, 7 is positive. If we let x equal -10, -10 minus 4 is negative. And then x plus 1 squared, when x is -10, that'll still be positive. And then lastly, x plus 6, when x equals -10, that's negative. So in the numerator, we end up with a positive. Once we multiply those together in the denominator, we also end up with a positive. So we see that the sign of r of x is overall positive. I'll do one more and then kind of just let you know what the rest are. You can check on your own. Let's check something on this interval between -1 and 2. So I'll test r of 0. So again, 125 is positive. And then 0 plus 3 squared is positive. 0 times -2 would be, or I'm sorry, 0 minus 2 is negative. And then 0 minus 4 is also negative. In the denominator, 7 is positive. 0 minus 4 is negative. 0 plus 1 squared is positive. And 0 plus 6 is positive. So in the numerator, we would end up with a positive number. In the bottom, denominator, we would end up with a negative number. So overall, r of x is negative between -1 and 2. So r of x would have negative values. It would be worth it for you to pause and confirm for yourself that r of x is negative between -6 and -3. It's also negative between -3 and -1. Just as a side note, that shouldn't be too surprising because the 0 of x minus 3 had a multiplicity of 2. So we knew that the graph would bounce off the x-axis there. You'll also notice that this vertical asymptote at x equals -1, on both sides of that, the graph is negative. The graph did not change sign. And that also comes from the fact that this factor in the denominator, x plus 1 squared, also was multiplicity 2. And so moving on, anything greater than 2, if you were to analyze the signs, you would see that the sign of r of x is positive, which means a possible graph for this function. Well, we might want to keep in mind the horizontal asymptote as we graph this. So the horizontal asymptote, we notice that the degree of the numerator would be 4, and the degree of the denominator would also be 4. So we'd have a 1, 2, and a 1. The degrees are the same, so our horizontal asymptote is 125/7. That's a positive number, so that makes me feel confident that my sign chart is right, because the long-term behavior is indicating that the function is positive. And so we would get something maybe like this. There was a vertical asymptote, the function was positive. We had a vertical asymptote at -6. The graph comes up, touches the x-axis at -3, bounces off, and approaches negative infinity as x gets closer to -1. And then the graph starts out near that that vertical asymptote again at x equals -1, crosses through the x-axis at x equals 2, but then there is that horizontal asymptote again of y equals 125/7. So I'm going to let that graph flatten out a little bit in its long-range behavior. So if we sketch this graph, it might be a little challenging, but we do see that it fits the sketch we had relatively well, and I added in, for your enjoyment, I suppose, the hole that we had found at 4, 7.